I'd like to welcome you today to an FDL challenge that addresses what I think is the most exciting question facing humankind. Are we alone? One of the biggest challenges that we face looking for life beyond Earth is that life and its imprint on its environment can be indistinguishable from features formed by non-biological processes. This year's Astrobiology FDL team have worked to develop tools, databases, and taken an important step forward in understanding how organic molecules that are formed biologically can be distinguished from those that are formed abiotically. I want to thank the FDL staff and the challenge team for giving of their time and creativity to this important quest.
Good morning. My colleagues and I are excited to share what we've been working on these past weeks at FDL with you. Hi, I'm JJ, and soon you'll hear from my amazing teammates, John, Timmy, and Aaron. But first, let's introduce you to our muse and fellow explorer. Imagine you're a dragonfly. Well, a special kind of dragonfly that's being built to hop from place to place across the surface of Titan, the largest moon of Saturn. It's the only other place in our solar system where we've observed liquids flowing across its surface. However, Titan's clouds and rivers are made mostly of liquid hydrocarbons like methane and ethane. More fascinating still, beneath the thick crust of ice is an ocean made predominantly of water. One of the main goals of Dragonfly is to search for potential signs of life. Among the instruments that it will use for this task is a mass spectrometer, which is capable of determining the molecules that are present in a given sample from the environment. However, on an icy world like Titan, where the average temperature is well below freezing, organisms would likely carry out metabolism and reproduction differently to what is seen on Earth. So this means that it might actually be pretty tricky to decide if what we observe is actually a sign of life or not. Our work advances the concept of an agnostic biosignature, a way to recognize life as we do not yet know it. By looking for specific features of the molecules it finds, one can tell us how complex the molecules in the mixture are. We can begin to form special fingerprints or molecular biosignatures, which can offer a more conclusive determination if it encounters strong signs of life. So what do we mean by complexity in this case? Well, we can look at the number and diversity of atoms that make up the molecule, the number and kinds of bonds that hold the molecule together. We can even consider the number of steps required to create the molecule. What we have set out to develop is a kind of threshold. Molecules below the threshold can be created by abiotic processes, while molecules above the threshold are too complex to be created randomly in larger quantities. The presence of these more complex molecules, we believe, could make the discovery of life elsewhere in our solar system more conclusive.
Just 8 weeks ago, our team accepted the FDL challenge to better define the concept of agnostic biosignature. We sat down together and set 3 goals for ourselves. The minimum goal was to curate a data set of molecules that are useful for the search of life for NASA and for the broader scientific community. The next target was to demonstrate how to use the data set and train machine learning models to speed up the computations and to infer deeper relationships between molecules and their reactions. The bold goal was to take this step further to estimate complexity directly from instrument data, for example, using the mass spectrometer on board Dragonfly. This is a critical step that would allow real-time autonomous decision-making during space missions. Today, on behalf of my wonderful teammates and advisors, I'm honored to report to you the progresses we've made towards achieving these goals. First, let's talk about the data set. For the past few weeks, we put our hearts and souls into creating this data set, which is the first ever designed to catalog molecular complexity and training machine learning models. We've collected molecules from many different sources, incorporated relevant features such as mass spec, while computing scores for complexity. This data set will be made available for NASA's future missions and for the broader community. Here, I hope to stress that dataset curation is really at the foundation of everything we do. Just like this iceberg, it is the invisible dataset below the water that keeps everything else afloat. With enough good data, you can then do something exciting and cool, That's what Timmy will show you next.
Thank you. As John suggested earlier, the machine learning part of our challenge consists of two similar but slightly different tasks. In both cases, we want to predict molecular complexity using a neural network. The respective inputs to the network, however, are different. In the first scenario, we predict the complexity directly from some formal representation of a molecule. For example, a string that describes the structure of the atoms and bonds. The main use case for the scenario is speed. Of course, there are classical algorithms to compute the complexity of a molecule, but these can be very computationally expensive, especially for larger molecules. Using machine learning to find surrogate models can help us to get good approximations in just a fraction of the usual time. To put a number on it, we are potentially talking about the difference between days and milliseconds of computation time. In the second scenario, we predict the complexity of a molecule from data that can be observed by the instruments on board of a spacecraft, specifically a mass spectrometer. Predicting molecular complexity from instrument data is exactly what we need if we actually want to use this in practice to search for potential signs of life. Nevertheless, to the best of our knowledge, inferring the complexity of a molecule directly from its mass spectrum is something that has never been done before. That is, until FDL 2022, when our team took on this challenge and started to train machine learning models exactly for this task.
Okay, and now's the point where you should be wondering, does this really work? Well, we have some good news for you today. Let's take the results and you can see for yourself. On the left side, you see two histograms. The black one is the actual or calculated complexity scores, and orange are the ones our model predicted. They agree pretty well, don't they? Now look at the plot on the right. You still see agreement between the true values in green and the predicted values in orange, but there's this interesting range beyond about 10 to 20 where there is some discrepancy. Now that's an interesting place to look, because if you compare that to the histogram overlaid there, we can see this happens due to a lack of training data in that range. Now, this range is especially interesting because it's very hard to calculate these values traditionally. This is where ML comes in. Also, these are molecules that are primarily important for life, as we know it anyways. The range of molecules here is a prime target for our continued research, because this isn't just a one-shot deal. Our model may not yet be flight ready. We're not flashing the firmware on Dragonfly just yet, but it's a strong proof of concept. It achieves a major first. We can go from mass spec measurements to molecular complexity and do so at blazing speed. We see an upwards of 400,000 times faster versus the standard calculation method. This is exactly what a probe like Dragonfly has to do. And the tools we developed to make this happen will be provided to the broader community. Tools built around a central concept, perhaps best described by Carl Sagan. The beauty of a living thing is not the atoms that go into it, but the ways those atoms come together. Thank you.